Good morning. Thank you, Shuba, and for the opportunity to be here with so many new faces. And so just before me, I think Darius have gave a great presentation on the mechanical aspect of inherent optical properties. So I will continue about the practical aspect of inherent optical properties. Before that, for people who don't know me, I was at UMass Boston. Now I'm at Xiamen University. So my research aspect or interest basically is a radio transfer and inversion algorithm and blah, blah, blah. Okay, so you are here me about for 2 days. Okay. For the IOPs we are talking about, basically is absorption properties and the scattering properties. I guess many of us or all of us have experienced that we have seen different colors of the water in ocean water or inland coastal waters. That's from the surface. In the water below the surface, actually, I think just a moment ago, Darius also showed that the solar radiation also changes with depth at the near surface. Actually, I did have a point. So near surface, the spectrum look like this. Okay, pretty much kind of balanced between blue and green and red. With the increased depth, you see the red photons go much faster than the blue and the green photons. And this for the ocean water, yes, Gulf Stream, and then this for the coastal waters, you see the big change of the solar radiation with the depth. In addition to that, just look at different angles. This is measured by Ken Walls. Okay, this upgrading readings just below the surface for different angles. Okay, this is basically different angle. You see also a change of these upgrading readings. All these actually, in addition to the solar input from the sun and the sky, the modulation is by the so-called inherent optical properties. So we have water constituents like phytoplankton, suspended sediments, dissolved organic matter, all those things. These will make the IOPs or inherent optical properties. Then work on the boundary conditions. I call it boundary conditions, basically the solar radiation from the sun and the sky, like say is early in the morning or noon time. These boundary conditions change. So the combination or interaction of these two then make the modifies or the color. Okay, what we see by our eyes or measured with the at different depths. So the inherent properties here, by definition, is a capability. Okay, regardless of these boundary conditions, basically, these are independent, two independent things. Okay, that's what this inherent mean. So as I said, it's the inherent for the ocean optics or ocean color remote sensing. What really matters to us is absorption and the scattering properties. I think Darius has given a good explanation about the mechanism for absorption. Basically, photons absorbed, the energy gone. Okay, no, we no longer see it. That's absorption. So basically, it's a transfer of energy. Then for scattering, it's just okay redistribute of the energies after heating by molecules or particles. So this is redistribution. Then for ocean color remote sensing, because we have our sensors look down from above, look at the water. Okay, so we care a lot, or we care mostly of the back scattering. So as you can see now, okay, scattering has angular sort of dependence, as explained by Darius. So for the practical aspect of inherent optical properties, we care about these coefficients. Basically, we care about the numbers and the spectral distributions. So by definition, it's a collimated beam hitting on this media, okay? Then these IOPs, these coefficients, is defined by this change of these energy. Okay, it's photons. See, this photons is this P and the P prime. Okay, this is the input energy. P prime is outside. Okay, what remaining energy. So this delta P, it's the difference between the input and output. Then the definition of the coefficient, that's what I want to emphasize, it's a relative change of this delta P versus the input P, because we can imagine if the input P is more, then this delta P could be also more. So what we care here about these coefficients is a relative change. In addition to that, as you can imagine, if this delta R is thicker, so that the change will also be larger. So this relative change is ratio to this delta R to get these coefficients. So that's a fundamental sort of kind of quantitative measure of these IOPs. But I have to also notice that this delta R has to be infinitesimal, okay, close to zero by definition of the inherent optical properties. That's a way to reduce the multiple processes of these kind of interactions between media and the photons. Think about if you have more scattering within this media, then that absorption there or scattering has a combination of both. So we have to try to by definition, ideally, this delta R has to be very tiny or very thin. Okay. So, however, the units we use for this A and B is per meter. That's because this delta R is measured. We use meter to quantify it. Also, maybe the actual delta R may be 0.001 meter. Okay, or basically it's 1 or millimeter, but we still use meter as a unit. So I always emphasize in my class, for our natural science, units is very important. We cannot ignore that. So then this absorption and scattering properties, their units is per meter. Okay. So as you can always see, A say it's a number 0.4, B is 1.5 per meter. It doesn't mean, okay, it's 40% of absorbed after a meter. It's not that. Okay. We just use this per meter as a way to quantify the capability of this media, its absorption or scattering properties. Again, so we have this absorption and the scattering, but scattering has a kind of angular dependence. That's what Darius also has mentioned. So what we really care about scattering is a volume scattering function, this beta. It has a units per meter per stereo. So I will get that stereo later. And here in this class, I will ignore the inelastic scattering, as Darius also mentioned, Raman scattering and or fluorescence. That will be ignored here. So here the focus is elastic scattering. From this volume scattering function, we can calculate the total scattering coefficient, this B. Okay, this basically the integration of the 4 pi solid angle, which expanded will be like a d theta d phi. I will get that later. I bet Mike Tatosik also will cover a lot of details in the afternoon about this. So from this A and B, we can get the so-called beam attenuation coefficient, which simply is a sum of A plus B. Okay, so basically, if you have a beam, okay, hit in a media, it will be absorbed, and some will be absorbed, some scattered. So for such a beam, the attenuation is the C. Okay, it's A plus B. So here now we see, okay, in the water, any natural waters, we have phytoplankton, we have dissolved organic materials, and we have suspended particles. So these will form the IOPs. And because by definition, we have this delta R close to zero, infinitely small. So by definition, IOPs are additive. So you have a chlorophyll's absorption, CW absorption, then the total will be simply those sum, okay, in addition to the water molecules. So generally speaking, we have A as A water plus many other dissolved or suspended constituents, and B the same thing. If we want to do it really in detail, that's what Darius have done this exactly 20 years ago. You have to put each one of these, their contributions. You have to estimate them, calculate them, then sum them together. This includes organic matter, corioles, virus, bacteria, then the different kinds with different sizes of phytoplankton and plus zooplankton. You have to put all of these into basically calculate each component, then sum them up. So this is what Darius did. Okay, basically you really have the kind of tools, you have the components, you can sum them up to with very detailed estimates. Like the phytoplankton, it's 18 kind of different pigments. Detritus, those are the dead kind of phytoplankton, minerals, and the sediments. You can do this. Okay, you can calculate each one of them. But practically, we just don't have those details. Okay, 18 different phytoplanktons. So you have to really get each one of their kind of numbers, okay, distributions, and their so-called average, the cross section. So we don't, 99.99% of the practitioners, we don't have those details. So what we normally do is a practical way to separate these different components based by filters. Okay, this is a blank filter. This is after you filter some water samples. As you can see, whatever captured by the filters, we call it particle. That's this AP. Okay, whatever passed this filter, get into filtrate, we call it gap stuff or dissolved or colored dissolved organic matter. It's the same thing, but different terms. Okay, so now you can see, okay, particles or dissolve, it really depends on the filter use, the pore size. Some filters has a pore size about, say, 0.75 micron. Some filters have a pore size maybe 0.4. So commonly what we use is a GFF filter that has a 0.75 kind of micron pore size. So now you can imagine anything pass through that 0.75, we call it dissolved. Whatever captured by this filter, then it's particles. So these are practical sort of kind of separation. Further, for these particles, we have those kind of live pigments versus dead particles. So we further separate the particle into APH, phytoplankton pigments, plus AD, we call detritus, those kind of dead materials, but captured by filters. So now you can see, okay, for this total absorption of water media, okay, ocean water or lake waters, we have A water, okay, pure water or pure seawater, APH, phytoplankton pigments, AD, detritus, those dead stuff, and then AG, gap stuff, yellow substance, color dissolved organic matter. So we have these basically 4 individual components as a practical way to decompose the total absorption coefficient. So the first and the most important thing is A water, because that's the fundamental thing of all the natural water. It's the water kind of holding these dissolved or organic or dissolved or suspended materials. So what's the value of A water spectrum? That's the first thing we have to know for human beings and for ocean color remote sensor or ocean optics. Interestingly, human beings have been looking for this, at least from my search, over 130 years. Back to 1894, that's 130 years ago, there's a publication by German scientist, Ivan, okay. His measurement is really kind of surprising to me. It's this red curve. Okay, this red curve in the blue, it's kind of higher compared to today's data, but in the kind of green to yellow, it's really kind of consistent or match very well with what we know today. That's 130 years ago. Okay, so with kind of better and instrument and more careful kind of preparation of pure water. Okay, because as you can imagine, what is pure water? The preparation of pure water is very difficult. So now we have more kind of data showing that this is Morales, I think 1977, and this red, okay, is Pop and Fry, and this the Manson, okay, 2016. Pop Fry and the Manson Fry, they are from the same lab. So now you can see even from the same lab, okay, they have the pure water absorption is different, okay, because of the instrument, the holder of for the samples and the preparation of the samples. So generally speaking, from visible all the way to short infrared, okay, here is the, okay, visible. It's in this range, okay, in this range. Then with the increased wavelength, as Darius also mentioned, basically water's absorption, pure water absorption increase dramatically. Okay, so visible is really low. Okay, with a minimum somewhere around 420 nanometers. Then with the increased wavelengths, so there's lots of order of 5. Yeah, here is the order of 5 of magnitude of difference. So then you can easily imagine. Okay, that's why we want to use the red, kind of infrared or shortwave infrared to do the atmospheric correction. That's because the absorption coefficient is so high in the longer wavelengths. But in the visible, UV to visible, still there are uncertainties. Okay, this is this figure from Popper Fry, 97. You can see this is the 1980s measurement. This is Tom Patel. This is Smith and Baker. This curve is from Popper Fry, and this one is from, let me see, Rootweld. Okay, so we can see, okay, even the 400 to 500, 400, 450 range, that's a factor of 10 variations in the just near past, okay, past 30, 40 years. Then we did something, instead of using laboratory samples to measure the pure water absorption, we use the IOPs, basically remote sensory reflectance, measured in the South Pacific gel. That's the clearest natural waters available on Earth. So what we estimate is the pure water, but this time, because it's seawater, so it's not a pure fresh water anymore, it's pure seawater. So we got an absorption coefficient in the near UV to blue as this blue, this green curve, this green, okay. So you can see in the 400 range, it's much smaller, okay, than the so-called standard Popper Fry, basically adopted by the community in the year 2000s, that range. So Popper Fry is this blue, so that's for fresh water, and this is the green, okay. So you can see that's a factor of 2 kind of a difference in the around the 400 nanometers. And this kind of, at least in the 400 to 500 range, match very well with another independent measurement by Cruz. That's 2011. Interestingly, after this publication, then a Fry's group measured the pure water absorption again with a different holder to hold in the water samples, which they think in the Popper Fry measurement, they use a spectrum, okay, as a for the whole system. So they think the spectrum, that calibration has some kind of errors. So their 2016 publication, pure water, fresh water, it's this green now. Okay, this blue is Popper Fry. So you see, in the shorter wavelengths, basically in the UV, there are factor of 3 to 4 differences, okay, for this range from the same lab, okay, but it's much smaller, okay, in the 400 range, and this red is our derived pure water absorption from the South Pacific gel data. So what really surprising or good to the community, we think, is that at least from 400 on, from 3 independent approaches, the pure water absorption, okay, is very close, okay, between this black, this red, and this green. It's almost on each other, okay, except the difference between this one, this black is for seawater, this green is for fresh water. So our explanation might be due to salinity, basically those salts, okay, dissolved salt. So this is a measurement by Rutgers. Okay, he shows that actually for the shorter wavelengths, the salt did, okay, increase the total absorption. So likely we think, okay, you go back to this curve, this data, okay, this figure, we think we are really reaching the point, have agreement on the pure water absorption from roughly about 400 on. Then below 400 nanometer, it's either measurement uncertainties or derivation uncertainties or due to salinity. So here we still have some kind of work to do to really fix this part, okay, about the basic UV part, about the pure water or pure seawater absorption coefficient. So that's after how many years? 130 some years. Almost how from back to from 1894 to 2016. So we finally, at least from 3 different groups, we have some agreement, okay, for the 400 to 500 range about the pure water absorption. In the near IR, okay, there are also some publications about absorption coefficients, like Hill and Quarry 1973, Segelstein 1981, Cole 1993. So they also show some differences in the near IR and the shortwave. Then we use some basically really highly turbulent waters, remote sensing reflectance, to look at the curvature. Okay, that curvature represents pure water absorption in the longer wavelength, because longer wavelengths, the absorption coefficient is so high, whatever the curvature of that remote sensing reflectance, it's an inverse of the total absorption. And basically it's pure water absorption. So from that analysis, we think the Cole 1893 at least match the remote sensing reflectance very well. So we think from this analysis, the Cole 1993 is the value to go for near IR and the 3 bands for pure water absorption. In addition to that, it has been found that pure water absorption changes with temperature and the salinity. And commonly it's expressed like this. This is A water, fresh at some reference temperature. Then this is the rate with change with temperature. This will change with salinity. However, for this psi T, there are contrasting values in the literature. As shown here, for I don't know how if I can pronounce this name accurately. Chapjerk, maybe. Okay, I could be wrong. And Hoscher's law, they show that okay, pure water absorption decrease with temperature, with the rate minus 0.00091. That's, in my opinion, that's really a big number. Okay, big number. But Pegao 1 year later indicates that actually this psi T it's positive. That means okay, pure water absorption increase with temperature. And the Rutgers 2014 measure again, he didn't find any kind of clear dependence of A water on temperature. To answer this, we use some satellite data, okay, trying to get some kind of understanding if it's really increase or decrease. From 20 years of MODIS, Aqua, for this location, this white box, which basically is the center of the South Pacific gyre, basically it's rather clears the natural waters. What we see is this is the temperature, okay, temperature increase from kind of November, October, all the way to February, okay, March. So an increase, there's a change of temperature by about 7 degrees, okay. However, if you look at total absorption of this white box, for this time span, it's nearly a constant for the 2 blue wavelengths, 412 and 443. So there's a big change of temperature, but nearly no change of total absorption. But for this location, actually, the contribution from CDOM and the contribution from phytoplankton is really tiny. Also, there are measurements from Breakout showing there actually not much of a change, or actually at least from heart measurements nearby. For this kind of so the oceanic waters, the phytoplankton also really do not change much, okay, for that time span. Then we did a kind of a simulation. If we use the decrease, basically use that Hoscher's law sort of kind of rate, then for that range of temperature, the total absorption will decrease by this much, okay. If we use Pegao's slope, then that total absorption will increase by this much. But this is absorption, this orange is observation. for Modis aqua. This is 412, this is 443. So basically from the observation of Modis, it shows a tiny decrease with temperature. So we think this reflects that actually pure water absorption, pure seawater absorption actually decrease slightly with temperature. And this, Shuban. Yes, we did. Yes, we did show that. By the way, I forgot to mention that as Shuba did. Okay, whenever you have questions, really please stop me. Okay, I forgot to mention that. Thank you very much, Shuba. So basically, that this decrease, and I think it matches with physics, because when you have increased temperature, density decrease. So basically, less water molecules. So that less water molecule, as shown in Rogers' sort of kind of study, that decrease of density, that rate, with this rate, okay, this slight decrease, it's generally consistent. So to this point, we think pure water or pure seawater absorption, at least for this temperature range, even higher, I don't know, okay. For this temperature range, it decreases slightly with temperature. Okay, that's about pure water absorption and pure seawater absorption. I need to check my time. Okay, that's 11. Okay, I have to be very careful about time. Okay, here about the particle absorption. Okay, from measurements, basically the spectrum of APs generally like this. Okay, and I think Darius also showed that you have basically you will see a strong peak around the center around the 440, 450 nanometer, another peak center around the 675 nanometer, also showing here. Basically, these are the contributions of curve A, and in the blue, actually, many other pigments I will show later. In the red, basically, that's the contribution of curve A from pigments. And then these are the total particulates. Then for the AD, okay, because for photosynthesis, it's not the total particles matters, it's the phytoplankton pigments matters. So we have to remove those dead stuff or so-called detritus. So these are the spectral shape, okay, of the detritus, as shown here with the increase, so basically higher in the blue, and with the increased wavelength, it decreases, okay. Generally, it's monotonically, and it is found also can be modeled very well with the exponential function, okay, with the exponential function, that's the AD. So exponential function with this slope, SD, roughly in a range of about 0.005 to 0.015 per nanometer. However, if you are really running into some kind of special time, inland or coastal water, you have really high sediments. It seems that high sediments have some kind of unique turning points, like one here, which cannot be well captured by the exponential function. So there's some kind of a statistical table seems much better for those kind of unique situations. So the difference of the AP and AD give us the APH, phytoplankton pigments. So that's the spectral characteristics of characters. Like here, this is AP, here is AD. Okay, so the difference gives us the APH. As you can imagine, okay, a strong peak in the blue band, and a weaker peak, okay, in the red band. That's 675 nanometer. So for this APH, generally the ways to separate them, okay, as Xiaoti did that is to look at the, I call it fightness, or the width of the blue peak, okay. This kind of picoplankton is really a sharp peak, okay, basically really very narrow, okay, spectral width for the blue. But for this kind of microplankton, as you can see, okay, this really kind of wide width, okay, for the blue peak. And also look at this ratio of the blue to red, it's much kind of smaller compared to the picoplankton. My understanding or interpretation of this, for picoplankton is too small. They have do not have enough kind of package to hold that many pigments. For this microplankton, it's large in size, so they can hold many other pigments. Okay, as I will show later. Also can be separated by species or groups. This can represent studies by DuPoy, okay, and Dearson. So you can see the coccolithophores as this kind of a spectral curvature or spectral shapes. And for these cyanobacteria, you see many kind of wiggles or zigzags or many peaks. And diatoms seems to have a kind of generally not much of feature. Okay, not much feature. These dashed line are specific pigments. Okay, and here for there's many kind of different. I think it's dinoflagellates. Okay, those sorts of things. So different species of phytoplankton can have different sort of spectral curvatures or shapes. But generally still, you see a strong peak in the blue and a weaker peak in the red. That's generally the common features. So as I mentioned a moment ago, the many pigments to contribute to phytoplankton absorption, as shown by this study. You can see this thick blue line, beta carotene, and this thin chlorophyll C1, C2, and here this black, it's this chlorophyll A. Okay, so you can see this chlorophyll A has this strong peak in this at a 675 nanometers. That's why when you see that a 675 peak, okay, you see this chlorophyll A absorption. On the other hand, if you don't see a peak at 675, then that phytoplankton must be dead. Otherwise, okay, it should be there because chlorophyll A is kind of ubiquitous. It's always there. So these are the you will kind of further decompose the phytoplankton absorption to various pigments, you will get this. I think yesterday there wants to talk about package effect. So we need to understand or to know this, okay, for phytoplankton absorption, package effect. What a package effect basically shows, okay, as shown in this figure. X-axis is chlorophyll A, the concentration, Y-axis is absorption coefficient. What we observe from this is with the increase of chlorophyll A, there's no linear increase of phytoplankton absorption. If it's a linear increase, the line should go like this. Okay, the line should go this. But I think you see it burned down. Okay, so it's not proportionally to chlorophyll. If we do a ratio, okay, of APH to chlorophyll, we call it chlorophyll specific absorption, you get this one. Okay, so basically increase chlorophyll, this ratio decreases. So that shows, okay, larger, basically higher chlorophyll, usually it's larger sizes of phytoplankton. So larger size, you have smaller or lower phytoplankton specific absorption coefficient. That's what package effect indicates. To understand this package effect, I did a simple sort of way to explain this. What is a bigger? This is a bigger phytoplankton. This is small phytoplankton. Here's a light. You can illuminating the two sort of kind of phytoplankton. Think about when light hit here, down below here, it's absorbed by the upper parts, then get to lower parts. If the upper parts absorb all the photons, then the lower part has no photons to absorb. Okay, so actually, the last way to look at this, absorption is a proportion to the cross section. Okay, so, but the concentration basically is a weight. Okay, the weight is proportional to the volume. Then your ratio of the absorption to the concentration is the weight. Then basically it's reduced to the area, cross area, divided by the volume. So it's an inverse of the diameter. So that shows, okay, with the size larger, the specific absorption will be smaller. Okay, that's what this package effect. So basically, size matters on efficiency. Okay, So that specific absorption coefficient, it's an efficiency on the absorption coefficient. Okay, that's about APAD and APH. Here gets to another important one, gap stop or color dissolved organic matter. I think that the earliest study about this is a book called 1981. It shows this wavelength, this absorption coefficient. Okay, this is in log scale. So you see a linear kind of function, log scale. And the later one, the Kirk, measures that in many kind of inland waters or coast waters, and basically shows an exponential decay of the Ag. Okay, so Ag is e to the s exponential function with Sg roughly about 0.01 to 0.03 per nanometer. Okay, Carter showed that this S also related to humic acid and this fulvic acid. So basically different sort of gap stop may have different slopes. But generally speaking, okay, this is a range of 0.01 to 0.03. As Mike did a nice work 20 years ago. That's publication in 2004. It showed the slope, okay, for different publications, actually there are more, okay, there are different ranges, okay, different ranges. More importantly, Mike shows that this slope really depends on the wavelength range you use to calculate slope, okay. If you use say level 520 to 600, in this range you will get a slope of this. If you get use a shorter wavelength, you get a kind of a bigger slope. So Mike suggests that instead of using exponential, maybe better use a power law function for Ag. So that's the power law number. So for this 6.92, basically it's no longer kind of a spectral range dependent, kind of applicable to the whole visible domain. I would think down the road for the community to do immersion, we should try to use this formula instead of the exponential formula if we want to extend it to the UV. Okay. So here is a kind of a summary of these sort of kind of ranges. So as I said, for our community or for this study, we have to have a sense about the numbers. Okay, so this is in Kirk's book. Basically shows this G is Ag at 400, 440. Okay, this P440 is APH 440. Okay, if I apply absorption at 440, it shows the general range. Okay, in natural waters, but I think he's more focused on inland waters. For oceanic waters, this will be smaller. Okay, but this gives us a sense. Okay, the higher values and the lower values. Another way to do this, okay, I always kind of play is in Excel file. You can get the spectrum, okay, of the A water. This blue, it's A water spectrum. This red is phytoplankton absorption. This green is a detritus plus gap stop, and this purple is a total. So when you play this sort of kind of different components with a different kind of proportions, then you will see how this total change with the different components. You get a feeling, okay, when it's ADG dominance, then how the A total will look like. When the APH dominates, then how the A total will kind of the spectrum looks. So that gives you a feeling of the spectrum. This is very important, as I always emphasize, for ocean color remote sensing. For ocean color remote sensing, we're not working on single band. We're working on the full spectrum. So we really need to have a good feeling how the spectrum appears under different kind of conditions or combinations. Okay, that's about absorption. Get to scattering properties. I think Mike will talk more about this. As again, okay, there are many materials in water. It will scatter, okay, including the coriolis, virus, okay, phytoplankton. And here are the kind of generally the size distributions. Basically, with if it's larger, the number will be smaller. Okay, if it's the diameter is small or small particles, basically number, the total number will be distribution will be higher. So this kind of generally follows in log scale follows kind of a linear function. Then in the a normal scale, it's a power law function, inverse power law function between the numbers and the diameter. So again, we can, because IOPs are additive, so you can divide this into many components. Okay, for the total B, it's B water plus the contribution of each individual components. BB do the same thing. Sorry, here should have a B water, BB, okay, BB water plus BB many components. Again, as Darius did, if you want to do a very detailed calculation for these scattering properties, you have the plankton, 18 types of plankton, detritus, and the minerals and the bubbles. Okay. For the scattering, then there are no yellow substance. The yellow substance is as molecules. That component is absorbed in the water part. Okay, because water scattering is also a molecular scattering, as Darius explained this morning. So the yellow substance or sedum, that part, the scattering part is absorbed into the B water. The rest is just phytoplankton, detritus, minerals, and the bubbles. Again, you want to do these calculations in detail, you have to know the components, okay, the detailed, like the numbers, okay, the basic density, cross-section of these individual sort of kind of constituents. We don't have that, or very few have those details. So what we do practically is to separate into molecules, quote unquote, particles. Particles, those, as I said, just captured by the filter, or whatever, just except molecules, we call it particles. In addition to that, well, bubbles, okay, you have wind, then there are in water there are bubbles, but that's for the for ocean color remote sensing, but also for ocean anyway, for all the natural environments. Okay, you have wind, you have bubbles in water. Also, another part we normally don't touch is turbulence. When you fly, you feel that turbulent sort of feeling. Then basically you are shaken. So also when you have a kind of temperature change, okay, of the in the water, then you also there are bubbles or the turbulence. So that's also will make the shake. So that's a turbulence. But normally we don't touch that in ocean color remote sensing. So for that, then we, instead of making B a sum of 20 some components, we have the total B as a sum of two components, B water and the BP. This is the particles, and basically this is are the molecules, including water molecules or all the molecules in water. If we want to go one step further, we can divide the particles into inorganic material and organic material. I think that's important for the management, because in the coastal zone, okay, the particles are organic, inorganic matters for the coastal management. So if we want to go one step further, it'll be good to separate the particles into organic and inorganic. Darius has mentioned that the scattering, it's a full space set. Okay, so really what we need to know is a volume scattering function of the part of the media. Okay, so that's it's represented by beta. Again, so you see this beta definition. It's phi is its energy at some angle. Okay, phi s. Phi I is an incident photon. Delta R is that infinitesimal thickness of this medium, and this delta omega, that's what differentiates from this volume scattering function from absorption, because we are counting the photons of energy in a small solid angle. Okay, so that's what this delta omega means. It's within this small range. Okay, with this small range of solid angle, how many photons get into that angle? And this psi, it's a scattering angle. As you can imagine, okay, this scattering angle could be very near forward or 90 degrees. So, so that scattering angle really matters for this beta. Depends. So we don't, as Darius showed, different scattering angle, you have different distribution of this scattered energy. So that's why this unit has in addition to the per meter, has a per steering angle. Okay, that's counting for this okay, solid angle into that direction. So from this Boltzmann scattering function, if we want to calculate the total scattering coefficient, then basically the integration over the 4 pi solid angle. So B is the integration of beta over 4 pi solid angle. From high school algebra, integration over 4 pi solid angle basically sine theta, d theta, d phi. Okay, then if you want to calculate forward part, that's from 0 to 90 degrees. So that's a forward part, so 0 to half pi. Okay, then you will get the backward part with half pi to pi. Basically, this is forward is 0, perpendicular that's 90 degrees, that's a half pi. Go backward, get to the angle of incident photon, that's pi. So that's for this theta. Okay. Another way to look at this direction of the incident photon. Okay. This is the kind of a latitude angle. Okay. This circle is kind of azimuth angle. That's a phi. Okay. This way is a theta. Okay. This wrong circle, that's a phi. So for the 4 pi solid angle integration, basically it's integration over this ring. Okay. For this ring, for that delta omega. Okay. So delta omega is delta theta and delta theta, delta phi. So think about for incident beam going forward, when you rotate, okay, rotate within this circle, because the photons have no idea why should go to this way or go that way. So in this azimuth angle, the possibility is identical. Okay, it's equal. So that's why in this point, that's a photon goes in. Okay, this is azimuth angle. For the azimuth angle, the photon can either go this way or go this way. So that means it's uniform in this direction. So that's why for the 2 pi solid angle over a 2 pi azimuth angle, the integration can be taken out. That's where this 2 pi comes from. That's because beta is not a function of this direction, okay, of the azimuth direction. But beta, it's a function of this theta, because if you close to theta versus 90 degrees, the possibility is very different. Okay, it's totally in other way, it's the distance from this angle to the incident beam versus this angle to incident beam. It's completely different. Other than the azimuth angle, as long as it's a circle, azimuth angle, you run a circle, it's the same. Okay, but for the latitude angle, okay, from vertical, from a little bit further and very bit close, that theta is very different. The distance is very different. So that the beta is a function of theta, but beta is not a function of this phi. So that's where still B will be an integration over the theta, not integration. So over this phi, that's why we can take this integration over 2 pi, get out. So that's where this 2 pi is. Then further, if we want to calculate forward scattering, basically that, then this becomes pi will be 0 to half pi. Basically, theta will be from 0 all the way to kind of perpendicular. Okay, that's a half pi, get the forward scattering coefficient. Then if you want to do the backward scattering coefficient, then it's basically from here, half pi all the way to pi. Okay, get to the direction of incident photon. So that's a way of calculate forward scattering coefficient and the back scattering coefficient. On the shape, okay, Boltzmann scattering shape of pure water or pure water molecules, as Darius mentioned, it's a radial scattering. So it's a minimum, it's a 90 degree, and maximum, it's either 180 degree or 0 degree. Basically here, this is the back scattering, this is the forward scattering. The reason at the smallest, at 90 degree, that's because of polarization effect. Okay, it's photons go in, photons are polarized, so 90 degree as some one component will be completely kind of gone. So that's why, as Darius also showed, it's 1 plus cosine square. So that's why this has a minimum at a 90 degree. That's because of polarization effect. Because of this kind of symmetry sort of behavior of the molecular scattering or radial scattering, then total B water, it's a 2 times, okay, of the backward or forward scattering coefficient. Basically, the forward scattering coefficient and the backward scattering coefficient is identical because of this symmetric shape. Then when you add the particles in this game, then the volume scattering function change dramatically. Okay, as shown, that's 50 years ago. 50 years ago. This is this 100 degree. Here is 90 degree. You can see this is a forward. Okay, this is backward. So we have particles because of this, as a mentioned, the mean scattering. Also because I think it's the diffraction. Okay, makes the forward scattering significantly stronger than backward scattering. That's many orders of magnitude stronger. Okay, than the backward. That with early days, Petzold has a really big instrument to measure the volume scatter function. And then later on, I think Mike and Schulman, they have their instrument to measure the volume scatter. This focus on the backward domain, right? But no, also 18 degrees. Okay, so okay, so this is a max measurement for the basically here. This focus on the backward domain. Okay, for the volume scatter function. And here another instrument by the Ukraine instrument. It measures roughly about, I think they claim 0.5 degree all the way to about 175 degrees, something like that. Also shows the same thing. Okay, forward scattering is significantly stronger, okay, than the backward scattering. So here's a way to basically, as shown in Mobley's book, this is these are the Petzold's measurement with basically showing the turbid water, coast water, clear ocean, pure water. Okay, for this chart, the x-axis is log scale. This basically is the same chart, same numbers, same numbers based upon x-axis changed to normal scale. As you can still, okay, basically shows the significant contrast between natural water and pure water in the volume scatter function. Okay, it's a common, sort of, as I mentioned a couple of times, particles strongly forward scatters. A number to measure this is called a backscattering ratio, which is BB over B. For molecular scattering or BB water, that's 0.5 because it's basically it's symmetric, so it's 50% forward and backward. But for natural waters, that is about 0.005 to 0.05, depends on the particles. And I think Mike will show more details about this. And here is basically a comparison, okay, of these volumes, the shape of the volume scatter functions. And Mike has shown that actually from this BB ratio it can be used to estimate the refractive index of the particles. If you're interested, I think Mike will show more of this. Another thing I want to get the attention is the mathematical sort of kind of a representation or description of this VSF, because we human beings always want to use simple math, okay, as simple as possible to describe natural phenomena. Okay, so here is I think used quite often in the early days, the Henry-Greenstein volume function. Basically, use one parameter G can very well simulate the phase function, okay, or part of particles, especially in up to I think about 110, 120 degree. But this function is not good, okay, for the backward domain, because generally this function it's a monotonic sort of decrease with increase scatter angle, increase with psi. So you can see, okay, for the natural water, as I mentioned, actually it bends back. Okay, after about 120 degree, it bends back. But this Henry-Griston function cannot bend back with the increase of the scattering angle. So later on, that's also quite a long time ago. Berkeley and Zaniewicz used this two-parameter sort of kind of model to get to trying to mimic or simulate the phase function. And this function, at least I played with it, it can do very good job for the large angles. Basically, can do very well for the to really turn back or to make an increase with the increased scattering angle for the backward domain. Okay, and Wells 93, this is really a simple function. Again, this is not good for the backward domain, but it's good for the small angles, basically for the forward domain. I think now the community take it's the Fourier-Forand more complex phase function has many parameters. Okay, and I think that's the one used in hydrolite. Yeah, the Fourier-Forand phase function, but it's at least to my eyes, is quite complex. Okay, compared to these simple mass functions, but it works much better. Okay, to really accurately represent measured phase function or volume scattering function. In addition to the angular dependence, there are also other. Well, here's another one. Sorry. Okay, this is a combination of the Koperevich one. Here, one is for, I think this is for the larger one. Okay, this for the larger phase function, or what is this is for the smaller one. Basically, if you have, basically he has tables for this smaller and the larger beta star. Okay, then you put a different volume larger one, volume smaller one, so can sort of kind of merge together to get the particles volume scattering function or phase function. So in addition to the angular dependence about the scattering or phase function, we also care about the wavelength dependence of these scattering properties. And I think Darius mentioned that for the molecular scattering, it's lambda 2 minus 4. But for seawater, for ocean optics, we usually take lambda 4.32 instead of the standard minus 4, lambda minus 4. This 0.32 is come from the change of refractive index with wavelengths, so that the ocean water, its refractive index is not a constant spectrally. There's a small change. Okay, for that, when that change is put into consideration, so this minus 4 becomes minus 4.32. But later on, Schiffer get to 4.17. I think this one is in Russian, so I cannot read it. So I don't know why he got 4.17. But anyway, so roughly it's in 4 point something, okay, in this range, not exactly minus 4. So that's wavelength dependence for pure water or pure seawater. In addition to that, salinity will add the value, okay, of this beta ratio or this volume scattering function or scattering coefficient. So I think from Morel's calculation, salinity will make it 30% higher, okay, compared to fresh waters. And that's volume scattering function. But if we want to, after integration, we can get the backward scattering coefficient of seawater. That's Morel's number. And later on, Zhang et al. Get smaller for the seawater. This is, I want to say that this number is at 20 degree and 34 PSU. So here's a code to calculate seawater or scattering coefficient for different temperature and different salinity. So you want to get to more accurate, you can run his code to get the spectral dependence of the pure water or pure seawater scattering values. This is 20 degree and 34 PSU, which is about 10%
smaller than Morel's numbers. The details, if you want to know, okay, you read this publication. That's about molecules or pure water or pure soil water. For particles, we have this is the early publication by Bricard. It basically shows, okay, B particles, it's a weak sort of kind of a wavelength varying sort of kind of function. Okay, and I think in many studies we simply use this power law function to describe the particle scattering spectrum or backward spectrum. Same thing with this eta, this power law coefficient roughly in a range of 0 to 2, and kind of in oceanic waters, maybe around 2, in coastal or inland waters, roughly around 0. So generally, it takes this form with weakly, okay, wavelength dependent compared to molecules. Molecules lambda to minus 4 point something, but this is lambda to minus 0 to 2. Okay, here is a study of a year ago from remote sensing. It shows that this eta roughly in the open ocean, maybe around 2. Okay, in the kind of coastal near inland, okay, really coastal water, roughly around 0. So it shows in that dynamic range. So here it's a contrast, okay, of the spectrum of BB, of pure water and the particles. So this blue is pure seawater, okay. Yeah, it varies with temperature and salinity. That variation is small. It's there, okay. But for particles, really depends on the numbers, the concentration of particles. At the open ocean, maybe particles, it's here, okay. Get the particles, BB particles. But for the coastal or inland waters, there are particles maybe here. So what this tells us, okay, for the coastal inland waters, the water molecules that is scattering, yeah, it's a minor player. Okay, it's a minor player. But for the open ocean, this is getting interesting. In the blue, it's really the water molecules making the contribution of backscattering. Okay, but in the red, actually, it's the particles making the contribution of backscattering. The reason I want to mention that when remote sensing, okay, we use blue, use green, and use red. Okay, at the same time, as just showed moments ago, the volume scattering shape of molecules and particles are different. Then, at different wavelengths, the impact to remote sensing, then it's no longer exactly the same. So we really want to get to more accurate, then we have to take account of this kind of spectral variation of which one is the major player for the backscattering coefficient for the oceanic waters. On the values, okay, basically for the pure water or pure seawater, it's roughly in a range of 0.001 to 0.004. Okay, quote unquote, we consider it constant. Many times we use as a constant. As you can imagine, okay, the BBP, then spectral shape, it varies, and this magnitude, B0, also varies. Depends on the load of suspended particles in water, also depends on the kind of particles in water. So bubbles, those are part of the bubbles. I think in the around 2000, there are many studies, especially with Martin Lewis group. They did a bunch of measurements. Okay, this is basically no bubbles, wind speed is low, and this is with bubble. After wind speed is getting high, so you can see, okay, quote unquote, although it's the same water, but when you have bubbles, the scattering coefficient increase a lot because bubbles will kind of, when photons hit on these bubbles, will go to different directions. This is the phase function, or the phase function of when you have bubbles. Okay, you can see this is a clean bubble. This is a coated bubble. So
with a study. Basically, you see that some kind of there's a bump, okay, roughly around the 70 degree. But further, you want to get further study or details of this, I suggest you go to this article. But spectral-wise, to our remote sensing, seems for bubbles do not show any spectral kind of selective sort of kind of enhancement. It's it's kind of white influence, not like the particles. Particle has a lambda 2 minus 0.22, so when it's 2 actually still blue rich. Bubbles seems so far okay. Haven't found any spectral kind of characteristics, so we generally consider spectrally flat. In addition to that, as I mentioned earlier, if we want really go one step further, we should separate the particles into organic, at least into organic and inorganic sort of kind of particles. You want to go further detail, that would be kind of follow Darwin-Stramsky. They divided that into detritus, mineral, and many kinds of phytoplankton. Here in this study, they showed that for organic, okay, this is called cross-section. Basically, it's kind of a scattering coefficient weighted by the weight. Okay, so you can think about it as a weight normalized scattering coefficient. So this is the molecule. This is the organic. Okay, this is the inorganic. What really shows here is that for organic particles, basically this cross-section is much higher, about 2 to 3 times higher than inorganic particles. Spectral-wise, roughly, at least from this study, not a significant difference. But on the cross-section or the normalized or weight or concentration normalized scattering coefficient, organic is much higher than inorganic. The reason is that the organic, the refractive index, it's smaller than the inorganic. Organic roughly maybe about 1.04, 1.03. I think Mike maybe show more about this. But inorganic is 1.08, 1.09. So basically that makes the inorganic has more backscattering coefficient than organic. Organic has more forward scattering coefficient. So that make, because forward scattering is much stronger a contribution to total scattering. So that makes the scattering coefficient of organic is much stronger than inorganic. That's the reason for this. Okay, that's about the organic and inorganic as kind of brief introduction. Okay, talk about these IOPs. I will spend a little bit of time talk about the case 1 and case 2 system, because when we try to model these IOPs or AOPs, it's common, okay, to adopt or at least to follow this kind of a system to do this. So that's why I think it's useful and important to share with you about this case 1 and case 2 system, the concept. As I mentioned yesterday, Schubert has shown this, that's 30-some years ago, actually really matters to ocean optics, ocean color. The major components are 3: phytoplankton, dissolved material or yellow substance sedum, and the suspended matters. Okay, but still 3 make it complicated. So in order to simplify this, there have been a system called case 1 versus case 2. There is a idealized line to separate case 1 and case 2, with case 1 defined as basically optical properties are in principle, okay, governed basically by phytoplankton. So that's the official definition of case 1. So basically it's phytoplankton, or which normally commonly is represented by chlorophyll concentration. So phytoplankton is a dominant matter, okay, to control or to form these optical properties of the whole medium, okay. So as you can see in this definition, there has nothing to do with location, nothing to do with chlorophyll values. Basically, it shows it's a relationship. That relationship says that, okay, phytoplankton is responsible for the variation of optical properties. So, but this is a qualitative definition. We don't know where to draw this line, okay? Because this is a kind of imaginary line between case one and case two waters. In order to really to go forward, be more practical or be used in ocean optics and ocean color remote sensing, we have to do modeling. Okay, so that's where early on, okay, Morel has done that. Okay, to model here, this is K, basically is KB. Okay, the attenuation coefficient, model K as a function of chlorophyll, as shown here, and this model, as Morel emphasized, that's what I read this title. Okay, in person, it's for case one waters. So case one waters are those waters that IOPs or AOPs can be modeled by chlorophyll concentration, as shown here. Okay, this is about K. Also, like C, also doing same thing. Model C as functions of chlorophyll. Okay, as function of chlorophyll. Also model BB as functions of chlorophyll. For many studies, this is Antoine's 2011 paper. Basically, in order to be able to do forward modeling or to do remote sensing or to do ocean color studies, we are trying to model these optical properties using chlorophyll concentration, because chlorophyll concentration has been measured commonly, routinely in the field surveys. So logic is when you know chlorophyll, then you can use these models to get the optical properties. So those are then, as shown here in Morel's 1888 paper in 2001, you have, when you know chlorophyll, you can get the KD spectrum, okay, KD spectrum for different levels of chlorophyll. Here's 0.03, all the way to 0.5, here's all the way to 0.3. When you know chlorophyll, you can also, this is the, so you focus on depth. This is chlorophyll. So when you know this is the integrated chlorophyll of the water column, okay. So you know the integrated chlorophyll, you can also estimate the euphotic depth. So this shows that, okay, further on here is also for when you know chlorophyll, you can get the total absorption spectrum and you can get the reflectance spectrum. So that this system really convenient, okay, to do the forward models of for the case one waters. So what that says, okay, for case one waters, when you give in chlorophyll, all other optical properties can be estimated, at least to the first order. As Morel shows, maybe that uncertainty, on average 20-30%, depends on the wavelengths. So that's a kind of practical way of going forward with the case one, case two system. So that also tells that case one water basically is one variable. Okay, you know chlorophyll, you get all kinds of optical properties. Okay, of attenuation, backscattering, even absorption coefficient. Not even single wavelengths, you can get the spectrum. Okay, so that's very useful and convenient. So then you back to this triangle. You see the qualitative separation is this line. Okay, somewhere. Actually, we don't know where that line is. Okay, somewhere. Basically shows, okay, here, for those waters, phytoplankton dominates. Okay, and the phytoplankton is the driver of the optical properties. But quantitatively, actually, we just use all the measurements available to do regressions. Okay, regression, get the regression line. So here, it's this point somewhere. Okay, somewhere in this triangle. So that's a quantitative sort of kind of average dependency of the optical properties versus chlorophyll concentration. In this case, so the quantitative case one is IOPs, AOPs are empirical functions of one variable, chlorophyll. Okay. But inversely, for global water, not necessarily any point or any location are case one. This is a study done, almost 20 years ago. It shows that from sea waves, for the 4 seasons, some of them in good agreement with that case one statistics, okay, to have the optical properties can be well represented by chlorophyll. Some open oceans, like even for this is the gyre, I think, it's kind of deviate from the statistics. So if you use the statistics as a kind of as a guide about the case one, then open ocean is not necessary really match that statistics. You do that to the UV, okay. See, all that statistics many times as in the visual bands, but UV bands, as we showed that a moment ago, UV, the absorption is governed by CDOM or gapstop, also by detractors. So UV is really highly dependent on the CDOM sort of kind of contribution. So the UV bands, as shown here, remote sensor reflectance, 360 versus 450, actually they do not follow exactly a one-to-one line. If it's just one variable, that should be really follow close into this kind of a single patch. But as I shown here, 360 or 380, this is open ocean. Okay, one patch goes this way, another patch goes this way. So that means this patch, the CDOM, relative CDOM versus this patch is very different. So that means, okay, for those open ocean waters, not necessarily follow the case one sort of kind of statistics. Okay, I think time is good. Okay, a few key points. As I mentioned, in addition to the boundary conditions, IOPs play the key role because as IOPs, the input solar radiation is same for water here, water there. But when we see different color waters, it's because of IOPs. They are modulating the incoming solar photons. The primary IOPs, absorption and scattering properties. Okay, and I have, as Doris showed in the morning, and we discussed this lecture, is scattering are angle dependent, okay, or direction dependent. And bulk IOPs, because by definition, they are kind of for infinitesimal sort of kind of media. So IOPs can be a lump sum of all the individual components. I think later on, we'll talk about AOPs, but AOPs cannot do this. It's only IOPs can be considered as a lump sum of the contributions of the individual constituents. And the absorption of pure water, pure seawater, now we think after more than a century, okay, we think we're getting very close to have a really agreeable or less uncertainty, I should say, okay, about the absorption coefficient of pure seawater or pure water. And also, we still have to maybe do more work on the UV part about the pure water's absorption, okay. And also, I think Zhang's work about the scattering coefficient of pure water along with the salinity and temperature, I think that pretty much get us to today to use about these so-called constants. Then in addition to the molecules, then it's for the absorption, we have the phytoplankton pigments, detritus, gapstop, or they have kind of especially phytoplankton versus the gapstop, they have very different spectral characteristics. For scattering, organic, inorganic bubbles, okay, and many times we just lump them all together, we call the particles, okay. It really depends on your focus. You really want to divide them, especially for kind of coastal study, you want to get to the organic versus inorganic particles, then you have to, we all have to spend more time or efforts on that to really on how to separate them remotely. And spectral-wise, water molecules, strong absorber in longer wavelengths, as I showed, with the increased wavelengths, it increase significantly, okay, especially in the near IR and the short infrared. And the phytoplankton, two unique peaks with a stronger peak in the blue, a weaker peak in the red. Detritus gapstop, basically it's a monotonically increase with the decrease of wavelengths. For water molecule scattering, okay, it's water molecule strong scatter in the blue wavelengths or shorter wavelengths. Particle scattering, It's weakly wavelength dependent, but I believe Mike will show more size dependence, composition dependence, and abundance dependence. I just mentioned about case one, case two. This is a very important concept in our ocean optics and ocean color system, remote sensing system. The definition is not based on location. So it's not simply, okay, oceanic waters will be case one, coastal water will be case two, because the definition is not based on that. Okay. So that tells, okay, oceanic waters could be case two, and the coastal waters or inland water could be case one. It really depends on if that relationship match with the statistics. Okay, I have listed a bunch of references. I will